All right, everyone. So welcome to the second review seminar. I've heard a few things and I've seen a few things about the first midterm. So hopefully we get to turn the ship around and follow course. And hopefully this review seminar helps you. Oh, by the way, if my hair is distracting, just ignore it. It's a bad hair day. Those of you on YouTube, you're not allowed to speak. We don't allow comments anyways, so it's cool. Right, so we're going to start with a few warm-up questions regarding PHP and combinatorics. This time around, I want to give you guys a lot of time to solve them. So the structure is you'll be doing these warm-up questions first, and then we'll talk a little bit about proof structures, and then finally we'll give you some proof questions, and we'll move on to the final topic, which is probability. Any questions? No questions? By the way, just like last time, I would be happy if you guys could sort of nod, wave, thumbs up, thumbs down, something. Okay? So let's start with question 1 or question 2, whatever you like. Is there a particular question you want to start with first? No? No preference? Okay. Let's just go in order. I'll give you guys maybe 5 minutes to do question 1. Okay, it's been about 5 minutes. Raise your hand if you think you're done with question 1. Okay, raise your hand if you think you need a little bit more time. How can it be both simultaneously? What am I supposed to interpret if you guys say no to anything? All right, I'm going to repeat myself. Raise your hand if you think you need more time for question 1. Okay, I'll give you guys a couple more minutes. Okay, hopefully everyone has had an ample chance to solve this. I will try to reinterpret and simplify what this problem is. There is a drawer full of socks. 20 of them are black, 20 of them are white. And Prithvi, your dear TA, doesn't have time to fold them in pairs. So every time he needs a pair, closes his eyes, quickly grabs a handful, and then finds a pair of socks with the same color from this handful. So the first question is, at minimum, how many socks does he need to grab in his handful to guarantee that he can make a valid pair of socks with the same color? Okay. First question, is this PHP or Combinatorics? Anyone? This is a freebie. It's PHP, right? So if it is PHP, what's the pigeon, what's the hole? Anyone? Yes?
The hole is the colors and the pigeons are the socks.
Yep. So you have these two, I guess, buckets, black and white. And the question is, well, the first question is, how many pigeons or socks do you need to pull to guarantee that at least one of the buckets will have 2 socks, right? What does the pigeonhole principle say for this? How many would you need? 3, right? Why 3? Well, if you could get away with 2, where you get both pairs in the same one, but what if you randomly picked 2 and you got a black and a white? you don't have a pair anymore. But now, since every hole or every bucket has one pigeon or respectively sock in it, regardless of what the third sock is, you'll end up making either a black pair or a white pair, right? So the answer, at least for part 1, is that you need 3. And this comes from the generalized pigeonhole principle, where if you have k buckets, in this case it's 2, and you have n pigeons, then you can guarantee that there exists at least one bucket or one hole where the number of pigeons is equal to the ceiling of n over k. Right? Now, our k, the number of buckets in this case, or the number of holes, is 2, and we want to find n such that this value is equal to 2, right? The ceiling of n over k is the number of socks in one of the buckets, and we want to make a pair, so we want to ensure that it's 2. We have 2 of the same color. Now, what value of n satisfies this? What's the smallest value of n that satisfies this? 3, right? 3 over 2 is 1.5. When you take the ceiling, you get 2. Okay? Now, applying the same logic, how much would you need for 7 valid pairs? 15, right? Wait, does 15 work? No. So we don't want 7 of the same pairs. We don't want 7 black pairs. We're allowed to have 7 of any pair. So now the arguments would sort of fail if you try to do, you want 14 in this to make 7 pairs of black. So you would have something like this, in which case you would want n to be 28. Right? And that doesn't guarantee that you'd get 14 of black. You'd get just 7 pairs of the same color. So an important point to note here is that this ceiling formula actually comes with a statement. And the statement is, given n pigeons and k holes, there exists a hole with at least ceiling of n over k pigeons. So we're not allowed to use the PHP rule directly, because if we were to apply that, we would be looking for 7 pairs of the same color, which is not necessarily true. We don't need that. So what's the intuition here? If I grab a handful of 3, I can make a pair, right? So let's say I did this. Now, once I have a pair, I can take that pair out and put it aside. What are you left with? You're left with 1 pigeon in one of the buckets, and you have 1 pair. How many more pigeons do you need to pull to guarantee another pair? 2 more. You already have 1, so you need 2 more. So every time you add 2 more pigeons, you'd get 1 more pair. So what's the general formula for m pairs? M equals 1. You get, this is pairs. This is, I guess, socks. And we know if we want 2 pairs, we need 5. What's the pattern here? Anyone?
Wait, doesn't this number 15?
It does. 15 is the right answer.
Oh, it is? Oh.
Yeah. Yeah. I was just explaining why applying this formula is not correct. Because applying this formula and equating it to 14 means you get 7 pairs of the same color. But you can have pairs that are, you can have 3 black pairs and then 4 white pairs, right? So you need to identify this relationship. Does anyone see a pattern here?
Yeah.
What's the pattern?
Like each time basically add 2, so it's basically 3 plus n minus 1 times 2.
Yeah, that's correct. So n equals 2m plus 1. Right? It's what you said, but simplified. In which case, if we want 7 pairs, if m equals 7, n equals 15. So you would want 15 socks. Right? So this is a sort of a mix of both. It's not just PHP. It's not just combinatorics. It's counting. Okay? All right. Last question, I guess. How many socks do you need to pull to guarantee that you can make a black pair? What's the worst case that can happen? 22, right? Worst case, you picked 20 white socks, but then you don't have any white socks. Then you need 2 more black socks. So worst case, it's 22. Okay, great. Question number 2 is fairly straightforward. It follows from what you've learned in class. I'll give you maybe a minute to solve this, and we'll just quickly mention what the answer is. Oh, by the way, if you have any questions regarding the interpretation of any of these questions, then feel free to ask, and ask early, because if you ask at the end of the allocated time, you won't have enough time to reinterpret and solve it. So if you're reading it and you seem like you don't understand anything, just raise your hand. I'll come across and I'll help clear things up. No, you're done with the second one? Are we all collectively done with the second question? Okay, cool. Who can tell me what the answer is?
I want to
Simplify, please.
10 factorial by 2 factorial.
Yeah, correct. 10 factorial over 2. Right? There's 10 letters in the word graduation, but A is repeated twice. So if you were to consider the A's to be different, right? Let's say one was an uppercase A and the other one was a lowercase a, then it would be 10 factorial. But you know in reality, you could swap those 2 A's and you'd get the same ordering of these letters. So you have to account for this, right? You account for it by slashing everything by 2. Questions? Yes. Sure. We could do that. So this would be permutation with the repeated items. So let's say you have something like this: AAA, BB, CDD, EE. Right? So there's 3 plus 2 plus 1, that's 6, plus 5, 11. If all of them were unique, you'd just have 11 factorials. But because there's repeated items, you have to divide by the factorial of of the counts for each of these. So it's 3 factorial, 2 factorial, 1 factorial, you can skip, 2 factorial again, 3 factorial, right? So I'm not sure if you've seen this in class with something written like this. Where you're trying to permute n items where there's k1 items of type 1, there's k2 items of type 2, all the way to ki items of type I. There's one restriction here. The sum of all of these ki's should be equal to n. Any number in, or any character in the word, or any item in the sets must belong to some type, right? And the permutation for this would just be k1 factorial, k2 factorial, ki factorial. Right? Okay. Any other questions? No? So try and do question number 3. You had a question, so please go ahead.
I want to ask that each of the puzzles like within each set are different. Like is puzzle number 1 different from puzzle number 2 within CS?
Yes. Yes. So there's a total of 20 different puzzles. They're grouped into two parts. There's 10 puzzles for CS, and there's 10 puzzles for math. They're all different. And
6 people, right?
yep, you and 5 of your friends means there's 6 people. Now you get the same item for solving any CS puzzle, right? So there's 10 stickers that need to be distributed to the 10 people that solved it first, and similarly there's 10 of the same card game. Okay, how are we feeling? Are we feeling confident that we know how to do this question? Do we need more time? Raise your hand if you need more time. No? Raise your hand if you know the answer. Okay, a couple people. So if no one needs more time, then we can start. By the way, the CMS Gala is an actual thing, right? It's happening end of this month. So I'm not sure the exact date, but the details are on the AMACSS socials, so Instagram and stuff. It's a pretty nice event. We did this last time. We had around 200, 300 people show up. I'll be doing the puzzle booth, so this is a real thing. So if you do decide to come, feel free to drop by on the puzzle booth. Right, on to the question. So there's 2 sets. There's 10 puzzles. And you have, for each puzzle, you have 10 of the same stickers as prizes. Similarly, you have 10 math puzzles over here. And you have some card game. It's the same one 10 times. And between you and your friends, you make up 6 people. So if we're trying to find how many ways we can collectively, if we solve all 20 puzzles, that means your group of 6 friends ended up getting all 20 prizes, even though they're repeated. How would you find the number of ways the distribution could go? Anyone?
I thought of like 6 to the power 10 plus 6 to the power 10.
Okay. And that is because?
Because like I thought that like in each of the CS puzzles, right?
You can assign one of the 6 people to it.
Yeah, and then like I added the same thing I added from the math side because I thought like the order didn't matter, you know, like.
Yep, that's fair. That's fair. So there's 2 parts. So let's handle. Okay, let's restrict ourselves to figuring out just for this, and then we'll figure out how to incorporate the fact that there's 2 different sets of puzzles, right? So you said we want to do addition over here, and then to handle this, we have to do 6 to the power 10. Now, it would be 6 to the power 10 if all the prizes were unique, right? But 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But let's say it's just you and your friend that are winning. In which case, let's say you. This is a valid assignment. You win the first 4, and then your friend gets the last 6. But your friend also getting the first 6 questions, and you getting the last 4, end up with the same results, right? We don't actually care about who's solving each particular question. We care about how the prizes are distributed. And in both of these cases, your friend gets 6 stickers and you get 4, right? So we'd be overcounting in this case because we don't care about the exact order. We just care about how many out of the 10 are you, friend 1, friend 2, all the way to friend 5. But it was a close try. So now, given that this is the case, what are we supposed to use?
Stars and bars.
Stars and bars. That is correct. So what would the stars and bars be? You have 6 friends.
Your friends would be the bars, and yours as the stars would be the stickers.
Okay, so if you were to interpret it as a summation, as an equation, what would it look like? No, that's the final answer. But what would the equation look like? We've seen this before, where you can represent the stars and bars problem with this. So if I were to say let there be variables where each variable represents the number of stickers won by you and then one of your friends, how would you write out the equation?
It will be x1 plus x2, x3, x4, x5, x6 equals.
Right? And then we know what the formula for this is, right? It's 10 plus 6 minus 1, choose either 10 or 6 minus 1, either or. Right? This would give you 15, choose 5. Okay, so there's 15, choose 5 ways for the stickers to be distributed by symmetry. There's also 15, choose 5 ways for the card games to be distributed. So what's the total ways things could be distributed? Should we add or should we multiply? Think about it in terms of dependence. Does how the stickers distribute depend on how the card games were distributed? They're completely independent, right? So when they are completely independent, you have to multiply, right? Here's a very simple example. There's 3 different coffee flavors and 5 different donuts. How many ways can you grab a coffee and a donut? Is it 3 plus 5 or is it 3 times 5? 3 times 5, because you're considering pairs. So you can represent the distribution of prizes as a total of 12 numbers, right? You have x1 through x6 for the stickers, and then let's say you have y1 through y6 for the card games. So these are all independent from this. All the x's follow this relationship, and all the y's follow this relationship, right? Okay. Questions? Okay, no questions. Did we all get this, by the way? Or is everyone comfortable with this concept? Could I get nods? Yes, no, anything? Okay, cool. So the final answer would be 15 choose 5 squared. Okay. Let's move on. Right. Okay. Before we move on to the proof section, on request of Professor Roei, I am to sort of give a broad overview of what the purpose of proofs are. Okay, so let me just pull up my notes. I have this somewhere. Right. What is the purpose of a proof? Can someone tell me? Anyone? I'm not asking for a definition. What do we use it for? It's convincing. Yeah, correct. So proofs, the purpose is to convince the reader that a particular statement is true. Now, how do we do this? We do this by showing a logical sequence of statements that start somewhere that both you and the reader agree upon and end at the final statement that you're wishing to prove. When I say logical sequence, I mean that every statement that you make follows from the set of statements that you've previously made, or from a set of statements that both you and the reader trivially agree upon, right? So the set of statements that all of you agree upon are, simple things. Like you agree upon addition, you agree upon division, all those basic axioms, right? So this is the purpose of proving something. And it's disproving something is the same thing. You're trying to convince logically that something isn't true. So what's important in this is your proof isn't to convince yourself, right? I take little to no convincing. If I guess something's true or false, I don't need justification. I believe in my hunch. But you want to convince some unknown reader who might be very meticulous. So you want your logical statements to be watertight, right? You don't want any mistakes in there. And that's what we're trying to focus on in this course. So let's say you have some statement S, and you want to determine whether or not it's true or false. You don't know, but you want, let's say you're trying to determine what S is, and you think it's true. So what sort of methods do we have to put this in this box? We've seen a bunch in this course. Can someone name one?
Yeah, you could say contradiction.
Sure. Contradiction is one. What is contradiction?
Contradiction is when, instead of proving that the claim C is true, you show that the claim not of C is false.
Mm-hmm.
And that way you show that your initial contradiction that you assumed is incorrect, and therefore C must be true.
Assume the contrary. And then you show a fallacy. Right? So assuming the contrary means just assume not of S. Whatever the opposite of S is, you assume that's true. And somehow, under this assumption, you need to come to using a sequence of logical steps, you need to come to a result that is false, right? So something like this would work. So you assume not S, and then somehow through some sequence of steps, you came to the conclusion that Sun is smaller than Earth. I doubt that's the case, but this is a fallacy, right? It's an agreed upon fallacy. If there was a logical way to get here, we know this is not true, so there's no way this can be true, right? So assume the contrary, come to some fallacy. This was a rather extreme example. You might come to the fallacy of 7 is the smallest prime, right? Which is false because you have 2, 3, and 5. So anything like this. So by way of contradiction. Sure. What's another one? Yes. Induction. Okay, we'll get to what induction is. So simple versus complete. Simple induction is also known as weak induction, and complete induction is also known as strong induction. More on this later. You can't use induction for everything. You want to use induction under certain scenarios, which we'll explore later. There's a few more. There's a couple more. Who can tell me one more? Yep. That's one. Direct or by cases. So if you have a statement that needs to be shown for all integers, but arguing just by assuming n is an integer doesn't work, or is a little bit harder, but somehow breaking it into primes and not primes, just even and odd. If it makes things easier, you could do that just as well. Okay, we're missing one more. This is a pretty important one. Yes? Contrapositive. Right? The contrapositive is used for, can we use it for anything? The contrapositive has a very special use case. You can only use it for statements that are of implications. Right? And over the course of 2 or 3 years, every time I've TA'd, when it comes to contrapositives, I've seen a lot of mistakes happen when you try to convert it. So I want to drill this in everyone's head. A implies B is logically equivalent to the complement of B implies the complement of A. This says if A is true, then B is true. This says if B is false, then A is false. Why? Well, if B is false and A was true, then A implies B would not work out, right? This is not a valid implication. So if this statement is true, then you know that the only way this statement is true is false, true, false, false, true, true. Which means, if you look at it from the other way, if B is false, then A must be false. Okay? So this is by way of contrapositive. When is this useful? Why can't we just assume A and then show B? When is doing a contrapositive useful? So in A implies B, you assume A, you show B. Here you assume not B, you show not A. Why would we ever want to do this instead of this? Yes?
For example, we would have an implication when some polynomial is, for example, odd, follows that some x is even. So make a contrapositive to show if something is odd implies one over.
Yeah, that's a good example. Some quick terminology. This is called the antecedent. This is called the consequence. But you want to use the contrapositive when it's easier to assume not B and show not A than it is to assume A and then show B, right? So when your consequent is very easy to negate and work with, and it's a general assumption that you can use, you would want to use the complement. Or sorry, the contrapositive. Questions?
Yeah, I have a question.
Mm-hmm.
Can you show us how to negate properly? Because like there's this question on the midterm first question, which was a contradiction question, where it started off with showing like for every n comma k something, and then there's like in square brackets p implies q. So we have to negate it by first negating the for every two that exists, and then we
That's
negate
correct.
the square bracket p implies q to p and not q. So I want to ask you that, do we negate the first initial for every statement because it applies both to p and q? Is that the reason?
Okay. That's a good question. So let's see if I remember this correctly.
Who's xk?
Was it the xk? Okay. And what was the implication? Does anyone remember?
So x1 into x2 until xk
Okay.
is greater than L. And then
What? There exists?
yeah, there exists xi. I can just pull it out just give me a second.
Something like this, probably. The kth root of n. Is this the right midterm question?
Yeah, there exists I element of k such that yeah.
Xi greater than the kth root of
yeah,
n.
there's k.
Okay, cool. So you want to show that this statement is true for all of this, right? Then to take the contrapositive, you do not need to negate this. To take the contrapositive,
No, the contradiction. Contradictory.
oh, you want to contradict this.
Yeah.
Okay, great. So you want to assume that this statement is false, the entire statement.
Yeah.
So you'd have to negate both this and this implication. But if you wanted to prove this true, then, and you wanted to use contrapositive, you would just need to flip this, right? So by way of contradiction, so this statement says pick n, pick k, pick x1 through xk, any natural number, and this statement is true. If you're assuming for contradiction, you want to show that there must be some selection of these values such that this statement is not true, right? So what is, there must be some assignment convert to? There exists, right? I'm saying for every possible assignment, that statement is true, and someone else is saying no, then my question to him is, give me an example, right, where this is not true. So if you were to assume for contradiction, the for all would become a there exists, and you want to show a case where this is not true, which means its opposite, its complement, is true, right? We'll see soon that disproving a statement is the same as proving its complement, right? Does that answer your question?
Yeah.
Great. So this goes back to the difference between contrapositive and contradiction, right? The for all is part of S. So when you assume the contrary, you are assuming negation of S, so you would negate everything. So the quantifiers will be negated, and so would the statement. Cool. Wow, a lot of ways to prove something. What about disproving something?
Just proof by counterexample.
Counterexample. That's basically the one method we know. But technically, you can disprove something by using any of these proof techniques for the complement, right? Disproving S is the same as proving not of S. So then once you come up with not of S, you're free to use any of this. So there's nothing special about disproving a statement. It's just proving the complement. Okay. And this counterexample only works. You're saying a counterexample because you're implicitly assuming that the statement is of the form for all. And to disprove it, you are just giving an example. But if the statement was there exists a person in this room, let's say the statement is there exists a man in this room that doesn't have clothes on, right? Then to disprove the statement, you'd have to show every man in this room has clothes on, right? You can't use a counterexample by saying, hey, look, I have clothes on, so every man must have clothes on. Okay. That's a little bit about proofs. Now we're going to focus on induction, and then we'll take a short break. Okay. So induction is a very powerful tool. what kind of statements do we use to prove induction? Or what kind of statements, what properties do the statements have that allow us to use induction? What are the quantifiers? Can we prove using induction using a statement on a statement that is something like there exists? No, we need a for all, right? So use for proving a statement for all x in the domain, or for all n in naturals. In that case, your variable would be n. Okay, there's something else that's also important. What is it? What allows us to use induction on a statement? Yeah, step by step, some sort of relationship between the truth value of some certain n or x depending on other truth values, right? So if the truth value of the statement, let's say you have a predicate s of n, if s of n depends on s of n minus 2 and s of n minus 3, then there's some sort of relationship that you can use, and you can probably come up with induction, right? You can come up with an inductive proof. If the truth value of s of n is independent of every other truth value of s of n minus 1, n minus 2, you can't use induction. There's no relationship. There's nothing that would allow you to show that if these two are true, then this is true, right? So you want to use induction in cases where you can see that there's a relationship between the truth values of the predicate for certain elements in the domain. Okay. Final step. There's two kinds of inductions. One is weak and one is strong. Who can tell me what the difference is? Yes.
Induction have the induction hypothesis,
Mm-hmm.
and we use it to prove the induction step.
Right. And the weak one also has an induction hypothesis.
The difference is that in the strong induction, you assume that it's true for all k less than equal to n, like up to
Mm-hmm.
n,
Mm-hmm.
and then you have to prove for n plus 1. Whereas in weak, you only assume it's true for n, and then you prove it's true for n plus 1.
Yep. So in terms of the domino arguments, in the weak induction, all you need is the last domino to fall for this one to fall, right? The one right before. But in the strong induction, sometimes weak induction is not enough, right? Let's say I were to lay out my dominoes such that at every step for this domino to fall, it needs 3 of these dominoes to fall. And then for the next one to fall, it also needs, 3 of these to fall, and so on and so forth. Then you can't use simple induction. You can't assume just one of these. One is not enough. You need multiple. So in strong induction, you assume that the predicates is true for multiple values. So all the values that you need to show that this is the case. When you're using weak induction, since you're only using one value, once you prove that the first domino falls, you can show that every domino falls. When you have multiple assumptions, you need to make multiple base cases, right? So for in this case, where you need 3 dominoes for this next one to fall, you need to make sure that the first 3 dominoes fall, right? So you need to make 3 base cases. Does that make sense? Questions? Okay, no questions. We'll have a short break, maybe 2 or 3 minutes. You guys can hit the washroom. If you have questions about this that you want me to answer privately, please just come up. just keep this open. It's annoying. Does anyone remember question 4? No? It was homework from the first review seminar. Okay. Don't worry, I'll give you guys more time to do this. But for question 4, can someone tell me what method we should use? Induction, right? It's a for all statements. But that means you somehow see some sort of relationship between the truth value or of the predicate. What would the predicate in this case be?
We said S.
Oh, let's not use S. Let's use P. Yeah.
That the sum of all the FS's of a set S from 1 to n would be n plus 1 factorial minus 1.
Right. So the sum of all subsets in, let's call it Q. Q is a set of subsets of n where no set has consecutive integers. So for those of you that were here for the first review seminar, this is sort of like the power sets, right? It's a set of subsets of n, but with the added constraint that any all the sets in Q don't have any consecutive integers. Okay. So for example, if n is 3, you would have 1 is fine, 2 is fine, 3 on its own is fine, but you can't have 1, 2, or 2, 3. 1, 3 is fine. Right? Okay. So Fs is equal to n plus 1 factorial minus 1. And what you want to show is that for all n in naturals P of n, right? The statement is true. So what sort of relationship did you see that you think it's induction?
I mean, the way I saw it was that, like, if you have a set with n elements, right, and then you try to find the subsets with no consecutive integers,
Mm-hmm.
then I feel that
Your induction hypothesis assumption would be making something about P of n minus 1, P of n minus 2, some sort of P of n minus something, right? So you're on the right track. Consider minus 2 and minus 1 and n. Within all the sets that don't contain consecutive integers, can you partition it based on whether or not that set contains n or not? Right?
yeah.
Any such subset could include n or it couldn't. So there's 2 cases. Try to explore those 2 cases. I'll give you guys more time to solve this. All right, I'm going to have to take this up. So has anyone been able to find the relationship between P of n with other values? Any guesses? What is P of n minus 1? Let's not worry about P of n minus. What's F of n minus 1? Or sorry. Let's call that summation on the left-hand side, the summation S and Q, Fs. Let it be defined for some, n. So in this case, it's defined for n. What can we say for n minus 1? What does it mean? It's the sum of all subsets of 1 to n minus 1 that don't contain consecutive integers. Right? So let's call that function g. G of n is that summation f of s, where s comes from q of n, where q of n was defined as that set of non-consecutive subsets of 1 through n through n. So if we break it into cases, what can we say about g of n? G of n contains all non-consecutive subsets of 1 through n, which include all non-consecutive subsets of 1 through n minus 1, right? So it's the case where we're not considering n at all. Okay, but if n is in the subset, what happens? Can I have n minus 1 also in that set? I can't, right? It's non-consecutive. So if I put n in it, I'm only allowed to have my rest of my elements be non-consecutive from 1 through n minus 2. Does that make sense?
Yeah.
Great. Okay. But this sum is different. This doesn't account for the fact that n is in that subset as well. This is just from non-consecutive integers from 1 to n minus 2. If n is also, if I add n as an extra element in all of these subsets, what happens? What does f change to? If 136 also had an n, then what would f of t look like? 324n squared. So it gets multiplied by n squared. And that would be for every single subset. So if you look at f, the f would also be multiplied by an n squared. So since every f would be multiplied by an n squared, you could take that n squared out. You're left with g of n over 2. Or sorry, yeah. And then this becomes this. We're missing one more case. We made one small assumption. There's another subset that contains n, but isn't accounted in g of n over n minus 2. Just n, right? So this is just n. This is contains n plus more. And this is doesn't contain n. This is pretty tricky. But so I don't expect you to come up with this, but I do expect you to understand this. So if you don't understand this, I will go over it again. Just raise your hand. No? Everyone's comfortable with this? Do you want me to explain this again? Okay, cool. So let's use an example here. Let's use 1, 2, 3, 4. Right? Now, what's the set of non-consecutive subsets? Sure, 1, 2, 3, 4. 1, 3, 2, 4, 1, 4. Are we missing anything? No, right?
I mean, are you like,
This is every single non-empty subset of this with non-consecutive integers. We're not missing anything. Now, my claim was partition it into groups, right? So the first group, which doesn't contain n, is 1, 2, 3, 1, 3. This is exactly the set of subsets from 1 to 3 that don't contain any consecutive integers, right? We already showed this. Now, let's take a look at the subsets that contain n. You have 4, which is n itself. And then you have 2, 4. And then you have 1, 4. And these is this case, right? These two correspond to this case. If you were to take a look at all non-consecutive integer subsets of just 1 and 2, what would you get? You just get 1 and you just get 2. But in addition, you have this 4. So the f of these sets are both multiplied by 4 squared. So you can take that out. Does this example help? Great. So you'd find this relation. This is the crux. This is it. Once you justify this relation, everything else is just filling in the gaps. So let's take a look at what the okay, this is fine. Let's take a look at what the framework of an inductive proof is. If the question doesn't have a well-defined predicate, you would define it first, right? In this case, we defined P of n. And now what we're trying to show is that for all natural numbers n, P of n, right? The first insight was to find the relationship. And we found a relationship between P of n and P of n minus 1 and P of n minus 2, right? So let's rewrite P of n actually. P of n is the statement that g of n, as we defined, is equal to n plus 1 factorial minus 1. And now that we know the relationship between g of n, we can assume P of n minus 1 and P of n minus 2, and then proceed. So how many base cases do we need? Are we just using g of n minus 1? How many values are we using in our sort of relationship? Over here. What do we have? The value of g of n depends on what? Yeah, depends on two values, right? That means you would need to show it for n equals 1 and 2 to be able to show it for 3. Once you show it for 1 and 2, you can use 1 and 2 to show it for 3, and then you can use 2 and 3 to show it for 4, and you can use 3 and 4 to show it for n equals 5, and then so on and so forth. So your base cases would be n equals 1, n equals 2. Is this true for n equals 1? The only set, non-empty set of 1 is just 1 itself, and its square is still itself. So 1 squared is equal to 1 plus 1 factorial minus 1. You're fine. It is true. Same thing for 2. The only two sets you have is 1 and 2. So 1 squared plus 2 squared is equal to 2 plus 3 factorial, 2 plus 1 factorial minus 1. Also true. Questions about this base case? No, you just plug and play. You'd find all possible sets in Q, and you do the summation, and you'd show that they are indeed equal to n plus 1 factorial minus 1. So now, what's the induction hypothesis? This is a little bit of an overkill. I'm assuming it for every value less than n that predicate is true. But in reality, I only need n minus 1 and n minus 2. But it's fine. You can still make this hypothesis. So now what do you have to show? What to show? You want to show that g of n is equal to n plus 1 factorial minus 1. Okay? And we know, so this is the goal, right? This is the goal. But what we know is this. We know that this relationship is true. And we also know that we can assume, according to that predicate, that g of n minus 1 is whatever, n minus 1 plus 1 factorial minus 1. So now, all we need to do is use this relationship and the induction hypothesis to get to that thing. So we start with the left-hand side, and we show that this is true. And now we apply the induction hypothesis to claim that this is n minus 1 plus 1 factorial minus 1 plus n minus 2 plus 1 factorial minus 1 times n squared plus n squared. This follows from the induction hypothesis. And then hopefully simplifying this will get you the right-hand side. Let's try it out. N factorial minus 1 plus n minus 1 factorial minus 1 times n squared plus n squared n factorial minus 1. I can take this n squared common, n minus 1 factorial, minus 1 plus 1 cancel out. Okay, this doesn't exactly look like this. What are we missing? What can we do further? You have n minus 1 factorial, and then you have an n here. Can you merge them to make it n factorial? Yeah? N factorial minus 1 plus n times n factorial. And then you can do one more thing. Who can tell me what it is? Yep, you can take the n factorial common. N factorial 1 plus n, or n plus 1, and then minus 1. And then what is this? This is just n plus 1 factorial. Right? That's it. You ended up proving the induction hypothesis. And the structure takes care of the rest. You don't have to show it for anything. You showed the base cases correctly. You showed the induction hypothesis correctly. Questions? Anything regarding the structure of this? No? Cool. Let's move on to question number 5. Prove that there are infinitely many prime numbers. Should we use induction for this? Do you think prime numbers have some sort of relationship between them?
Yeah, I mean, I could do this using contradiction.
Yeah, that seems like a much more reasonable way to go about it. What would the contradiction be?
So assume that there are finite number of prime numbers, say n.
Okay.
So I say you have n prime numbers,
Mm-hmm.
and then like I multiply all of the prime numbers by each other.
Okay.
So whatever number I get is as that we know would not be prime because it has all the prime factors, right?
Yep.
But then if I add 1 to that number s plus 1,
Mm-hmm.
that number would be prime because that number won't be divisible by any of these prime factors.
Yep.
Therefore, now we've shown that that number, say s plus 1, is prime, and therefore now there are n plus 1 prime numbers, which contradicts our initial assumption.
That's perfect. So assume for contradiction there exists finitely many primes, finitely many primes, prime 1, prime 2, all the way to prime n. Consider capital P as the product of the primes plus 1. Now we claim that P is also a prime. What allows us to claim this? To make sure that to claim that P is also a prime, we need to make sure that regardless of what prime number we divide it by, it doesn't have a remainder of 0. And lucky for us, the remainder of the product of all the finite primes plus 1, regardless of what prime you divide it by, is just 1, right? 1 is not a prime. So these primes start 2 and forward, so 1 is a valid remainder. But wait a minute, that means that P is also a prime. Is that enough? We need to show something else about P too.
Well, that's enough because
Sure. This implies P is prime. But why can't P just be equal to one of these?
P is greater.
What if P ends up being equal to P10? We need to show one tiny thing. It's a formality, but we need to show that P is not equal to any of these primes. So it's a new prime, right? And that's trivially true because P is a product of these primes, and all of these are positive. So there's no way that P is equal to any of these. In fact, P is greater than all of these. So P is a brand new prime, which contradicts the fact that there's only n primes, right? Because we showed another one. Good. Okay. Any questions about this? No? Great. Question number 6. Before you guys start, please read it and tell me what proof method we should use. Okay. Is there someone else that has a different proof method they want to use? No? Everyone agrees that contrapositive is the way to go? What makes it a good method? What makes this statement, what allows us to use contrapositive for this statement?
It's easier to work with n not being prime than 2 to the power n minus 1 being prime.
Yeah, it's easier to work with n being composite and then showing that 2 to the power n minus 1 is composite than assuming 2 to the power n minus 1 is prime. Also the fact that it's an implication, right? Otherwise you can't use contraposition. Okay. What's the smallest composite number that we know of? What's the smallest natural number that's not a prime? 1 is not a composite. It's a composite of what? 4, right? So try it out with 4. 4 is composite. What's 2 to the power 4 minus 1? 15, right? Its factorization is 3 and 5. You could try it with some other values to see it, but I believe the result here is a little hard to get to. So I wanted to focus on identifying the right technique. This is actually the crux of your work. If you identify the right technique, the proof is going to be very easy, right? This particular proof requires something that you might not know, so I'll go over it. We can skip this. But in general, in your exams, identifying the technique is more important, because afterwards, if the technique is right, it should be pretty straightforward and intuitive on what you need to do. So n being composite, assume n composites. So it means a few things. It means n greater than or equal to 4. If you consider 1 to be a composite, then you'd have to assume, you'd have to show this separately. But what's 2 to the power 1 minus 1? It's just 1 again. So if 1 is composite, then 1 is composite is whatever. It's a useless statement. So n is greater than or equal to 4, and there exists natural numbers a and b, such that n is equal to the product ab. Now somehow we need to use this to show 2 to the power n minus 1 is composite. Two to the power n is 2 to the power ab minus 1. Oh, you can't see this over here. Can you guys see this? Okay, cool. So this is a factorization that works. I guess the best way for me to show it would be using the example of 4. 4 is a composite. It's 2 times 2. 2 to the power 2 minus 1, which is 3. 2, 2, 1, 2, 2, 0. 2 squared is 4, 2 to the power 0 is 1, this is 5. But this is the argument you would make. You would make that if n can be broken down into a and b, then I can factorize it like this. You'd also have to show that these factors are, none of these factors are equal to 1 or n, right? But yeah, something like this. You haven't learned this, you don't have to know this, but in your exam you'd get something similar, where the proof would use something that you do indeed know. Questions? You don't need to know this, right? But your version of a question that requires you to solve it, or is best solved using contraposition, would have something that is easier than this, right? Did you have a question? No, okay. Great, so that's it for the proof section. Now, I know your midterms are mostly proof-based, right? So it's really, really important for you to practice and understand these proofs. So make sure you understand the structure, and then once you understand the structure, try to use the structure and apply it to some problems. Your question bank is massive now. You have a lot of assignments and a lot of extra practice questions. Go over them. It's worth the effort. Okay? Cool. Now, we're going to move on to this last section, This is my favorite section. This is probability. I'll give you guys about 2 or 3 minutes for doing question 7, and then we can take up the answer. Okay. Is there anyone that needs more time? I don't want to rush it, so we can go over 5 if need be. Is there anyone that is still in the process of solving this? No? Okay, cool. So according to this hint, who can tell me under what condition that statement is false? What makes this statement false? When is an implication false?
When the E statement is true and the Q is false.
Okay, cool. So A implies B is false when A is true and B is false. So when is this statement false overall?
I don't think it could be false.
Why not?
Because like, say if x1 is true, right?
Okay. So you want x1 to be true, and you want this to be false, right? And when is this false? When this is true,
Yeah.
and this is false.
Yeah.
And when is this false? When this is true, and this is false. It's possible,
Yeah.
right?
Yeah.
So what needs to happen for this entire statement to be false?
It's to alternate between true and false.
Does it need to alternate? You have true, 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 and false. What needs to happen? Does anyone see, I guess I'm going to use A48 language, the recursion here?
All of them have to be true until the last one.
Yes, because to make the entire statement false, antecedent true, precedent consequent false, and this itself is of a similar structure. So then again, this needs to be true, false, until you can actually assign one of the Boolean variables a false. Okay, so let's see. A statement is false when x1 through xn minus 1 are true and xn is false. Great. So now, if we're talking about the probability of the statement being false, how do we find the probability? We know that each of these variables are independently, randomly chosen to be true or false. There's something implicit here, which I wish to mention. When people say randomly, they usually mean uniformly. Okay? So it's implicit in this question that the probability of me choosing for any particular value true is 50%, and for false, it's 50%. So what is the probability that x1 equals true and x2 equals true and so on and so forth, xn minus 1 equals true and xn equals false? What is this probability? What do we know about independence? Anyone? We've seen this in class.
1 by 2 to the power n.
Yep. Okay. I think you're correct, but you're jumping the gun a little bit in terms of the logical sequence. How can you simplify this?
P of x1 is equal to true into P of x2 is equal to true.
Correct. By independence, if the probability that x1 is true and x2 is true is equal to the product of the individual probabilities that x1 is true, right? So this probability is actually equal to P of xi equals true. You would take the massive product of all of this, n minus 1, and finally times the probability that xn is false. Now, since each of these variables are chosen at random from true and false, it's 50-50. So the probability that xn is false, 0.5. The probability that xi is true, 0.5. So, where are we? We're currently finding the probability that the statement is false. And it turns out that the statement is false with probability 0.5 to the power n minus 1, because we're multiplying it n minus 1 times, and again multiplying it by 0.5. So this simplifies to this, half to the power n. Okay, but that's the probability of this statement being false. So what's the probability of it being true?
1 minus 1 over 2.
Yeah, just take the complement. And probability of statement equals true. 1 minus 1 over 2 to the power n. Questions? No questions? Is everyone comfortable with this notation and all of that? Yeah? Great. I'll give you guys some time to do question 8. It's fine if we go a little bit over, right? We'll probably end up going 10-ish minutes over. All right, are we ready to do part 1? Yeah? Okay, let's do part 1. So the question is, you have 3 coins, 2 regular coins, fair coins, 50-50 chance of heads and tails, and 1 coin that always lands heads, right? Both sides of it are head. We're picking a coin randomly, we're closing our eyes, and let's say you can't differentiate between the 3 coins, so we're just picking randomly, we're tossing the coin. What is the probability that it landed heads? Does anyone have an answer? 2/3 is correct. How do we actually solve it?
So you do 1/3 into 1/2 plus 1/3 into 1/2 plus 1/3 into 1. So basically,
Cases.
it's first.
Yeah. Yeah, good. So you have cases. What's case 1?
Did you get 1 regular coin?
Coin is regular.
Yeah.
Let's use coin is regular. So we're going to do this, all right? I will write the probability of heads as this sum, and I will show you why it's true, all right? So the probability of heads given regular coin plus the probability of heads given not regular coin or 2-headed coin. Okay? There's only 2 cases. So either the coin was regular and you landed a heads, or the coin was 2-headed and you landed a heads. And why is this equal to the probability of H? We can actually use the formula that we know to expand this. Probability of head and regular over probability of regular plus probability of head and 2-headed given the probability of two-headed. Turns out when you simplify all of this, because the probability of the coin being 2-headed is 1 minus the probability of the coin being regular, it will cancel out and you just get the probability of head. Okay? Yeah, okay. Great. So this is something that you should know. Probability of A is equal to the probability of A given B plus the probability of A given B complex. Right? So we're using that. Wait, actually we're missing one thing. The probability of the coin being regular. And then in this case you're missing the probability of coin being 2-headed. Okay. So if the coin is regular, what's the probability of you picking a regular coin? Out of 3, 2 of them are regular, so 2/3. And what's the probability of tossing a heads, knowing that the coin is regular? 50-50, so it's 50%, so it's half. Right? Similarly, what's the probability of the random coin you picked being 2-headed? There's only 1 such coin out of the 3. And what is the probability of you landing heads when it's a 2-headed coin? It's 1, it's 100%. Okay, so overall, you get 1/3 plus 1/3, which is 2/3. Right? Let me just reiterate the formula I showed. I made a small typo. Don't want that to stay. Probability of A is the probability of A intersects B union B complements. This is just everything, so it actually doesn't do anything. It's probability of A intersect B union probability of A intersect B complements. Probability of A given B times the probability of B plus the probability of A given B complement times the probability of B complements. This is how you arrive to this this equation that we ended up using. Right? Cool. Part 2 says you do the same thing. You pick the coin at random and toss it, and it got heads. But instead of asking the probability of it being heads, the question is, what's the probability that it was the two-headed coin? Now, without doing any calculations, can someone tell me what this is? You can look at just this final line and tell me what this is. This is for regular. And this is two-headed. Sorry, what did you say?
1/3.
Why do you think it's 1/3? We're conditioning on the result being heads. So what we're actually asking is, out of the probability, whatever it is, of it being heads, how much of it, what proportion of this 2/3 came from the two-headed part? So what proportion of 2/3 came from the two-headed part?
I mean half, sorry.
Half, right? We're talking about proportions. So half of this 2/3 came from the two-headed coin. So it's half. Okay? So that's the intuition behind it. The question is asking, what proportion of this probability came from the two-headed coin? And we just take the ratio. So we take 1/3 divided by 2/3, and you get half. But if you don't want to do that and you just want to use the formula, we're asking for what is the probability two-headed given heads. And there's a small little trick we can do here.
Probability of two-headed intersection by probability
Two-headed and heads divided by the probability of heads.
and that is 1/3 into 1. So that's 1/3 upon 2/3.
Mm-hmm.
Should give you 1/3.
Yeah. Does this make sense? Yeah? Cool. Well, that was the last question of this review seminar. Thank you all for coming. You guys being here is a testament of your will to do well in this course. And hopefully this review seminar was helpful. This is recorded, so if you guys want to revisit it, just watch the video. If you have questions regarding this, you can reach out to me on the AMACSS community Discord. And I've also been graciously added by Professor Roei onto your Piazza. So if you make a question titling, a review seminar, I'll be able to answer it.